Perspective Class 5 Video 2. In this video we're going to talk about vectors in three-dimensional space. So let's go straight to the definition of what a vector in three-dimensional space is. So analogous to the two dimensions, if I give you an ordered triple of numbers, you could interpret this as a coordinate or you can interpret it as a vector. And the vector interpretation is simply you consider this a straight arrow with the tail at the origin and the head at the point corresponding to ABC. Okay, so directly analogous to what happens in two dimensions. Let's look at a picture of a vector right now. So this here is the vector 2, 3, 4. That's what this arrow is right here. It's the vector 2, 3, 4. It starts down at the origin, and that's where the tail is, and the head of the vector is at the point 2, 3, 4. Okay, directly analogous to two dimensions. It's just harder to draw. I mean, like, ironically, when you're drawing three-dimensional stuff, you know, you need to take perspective into account. Like, implicit in the way I've drawn this three-dimensional space, I'm representing three-dimensional space on two dimensions. So I've chose a way of representing three-dimensional space on two dimensions, and it's not 100% clear, right? You have to get used to reading these sort of diagrams and to thinking in this sort of way. But this is what a vector looks like in three-dimensional space. Exactly like in two-dimensional vectors, there's scalar multiplication. So if you have a three-dimensional vector and a scalar, again, a scalar is just some number. It's just whenever you're talking about vectors, you call numbers scalars. Then you can do scalar multiplication of the vector. So lambda times v is lambda times abc, which is just lambda times a, comma lambda times b, comma lambda times c. So you just do them all one at a time. Lambda times a, lambda times b, lambda times c. Okay? And we also have a notion of three-dimensional vector addition. So if you have two vectors in three dimensions, you can add them up, and this is what you get. And it's the same like principle as two dimensions. You add the first coordinates, you add the second coordinates, and you add the third coordinates. So you add them coordinate wise. Okay, this is three-dimensional vector addition, and not that we need it in this course, but I imagine that it's pretty obvious how you can generalize this notion to even higher dimensions. Like, you can define vectors in like 4 dimensions or 5 dimensions or as many dimensions as you want, and notions of scalar multiplication and addition, vector addition, they still work, but we only will be needing vectors in 2 dimensions and 3 dimensions in this course. Okay. One thing I want to say is the geometric interpretation of 3D scalar multiplication is exactly the same as the 2D scalar multiplication. So what I mean by that is you're considering things like lambda times v, okay? And the exact same theorem which held true in 2 dimensions still holds true in 3 dimensions. So in particular, like if lambda is positive, then you don't change the direction of the arrow. But if lambda is negative, then you flip the direction of the arrow, okay? And if lambda is bigger than 1, then you stretch the vector. If it's between 0 and 1, then you shrink the vector, and so on and so on. All of that theorem holds exactly true for three-dimensional vectors as well. Okay, let's do a quick example of some vector addition and scalar multiplication. So sometimes I forget to do the dot. Okay, like if there's not a dot there, then that's because I forgot to do it. But it's not the end of the world. You still know what I mean. So what is this? This is going to be 2 times 1, comma 2 times 0, comma 2 times 4, plus 3 times 0, 3 times 2, 3 times minus 1. Which is equal to 2, 0, 8 plus 0, 6, minus 3, which is 2 plus 0, 0 plus 6, 8 plus minus 3, which is 2, 6, 5. And that's the answer, okay? So it's honestly not significantly harder than in 2 dimensions. It's just you have one more coordinate to keep track of, okay? But the principles and the techniques are exactly the same. So this is how you do this sort of linear combination of vectors in 3 dimensions. The last thing I want to talk about is the line generated by a vector and the ray generated by a vector in 3 dimensions. So the line generated by a vector ABC is the line obtained by taking all scalar multiples of the vector ABC. And the ray generated by a vector ABC is the half line, or the ray, obtained by taking all positive scalar multiples of the vector ABC. So I'm not going to spend much time on these because these are exactly the same definition as in the 2 dimension, except in 2 dimensions we just had AB instead of ABC. But otherwise it's exactly the same definition, right? So this is the notion of the line and the ray generated by a vector in 3 dimensions. And if we just quickly do an example of this using the picture I drew up here. So the ray generated by this vector would be this ray right here, where it carries on going forever, infinitely. And the line would be where it goes in both directions. The line would also extend through the origin in the opposite direction. Okay, that's the end of that example, and that's the end of this video.